Algebra 2, Chapter 16, Section 3, Matrices and Vectors. So we're going to talk today about vectors. A vector can be thought of as a single column matrix. Okay, so you can also think of a vector as an ordered list, but it's most convenient to think of it as a single column matrix. Vectors are often written with an arrow over the vector, like this. You could also have a vector v, and we can make it 3, 7, and 5. Okay, and these entries in the vector generally represent some ordered item or perhaps even a coordinate like x, y, and z. Okay, so that's basically what a vector is. So we can think of a vector as a single column matrix. Because of that, we can use matrix multiplication to multiply a vector in a matrix, because a vector really is just a kind of a matrix. Okay, but we like to call them something different. A vector, of course, only has a dimension. It's like an n by 1 matrix. It has n rows and 1 column. So that means we can multiply by any kind of m by n matrix. We can multiply by this vector n by 1. Okay, generally though, we'll multiply, we're dealing with vectors, by n so that the output is another n by 1 vector. So you can think of this n by n matrix as almost like a function. When we multiply, we'll get another n by 1 matrix, which is really another vector. So let's do some examples. So I'm going to look at the book here and just do an example straight from the book. So if we look at example 2 in the book here, it says, suppose that the employment in a town in year t0 is described by a vector. So the vector is g sub 0, and this is the employment in a town. It's given as a vector 8,000, and the book puts 8,000 comma 400. So we can write the vector as an ordered list, but when we're using it as a matrix, it has 1 column and n rows. So I usually will write it in this way. And I keep forgetting that the book doesn't use brackets. It uses parentheses for matrices. They are both very common, so it gets confusing. Okay, and that each year, 2% of the employed people become unemployed, and 10% of the unemployed become employed. Okay? Find a matrix M such that G1, the employment after year 1, given by taking M, the matrix, by times G0, equals G1. Okay, so if we think of this as an equation, the employment for the employed, so this vector means employed people and unemployed. I don't think it's explained that very well. Okay, so E1, the number of people employed after a whole year, will be, so that we'll have 98%, 2% of the employed become unemployed. So that would mean 98% of the employed stay. So 0.98 E0 will be E1, plus we gain 10% of the unemployed people, 0.10 times the unemployed from year 0. And the unemployed at year 1 will be the 2% of the employed people that became unemployed, plus the 90% of the unemployed that we retained from the first year. And if we think about how to write this in vector form, we would have the employment and the unemployed, this vector would be, and then the matrix would be these coefficients, 0.98, there's no plus in the matrix, 0.1, 0.02, and 0.9, times the employment, the initial employment and the unemployment, which is this vector that we started with, 8,400. So one of the reasons that we do vectors is that we can write a lot of math in one simple statement. So we can represent a very complicated system in a simple way mathematically, and that allows us to manipulate it from a system level. And we don't get into that much in this class, but we're just kind of touching the surface of what we can do with a matrix and with vectors. So we could find G1 doing matrix multiplication here. It would be 0.98 times 8,000 plus 0.1 times 400, and we can just pull up a calculator. So 0.98 times 8,000. Remember, we're going, take the first row, the first column. So this E1 is going to be 0.98 times 8,000 plus 0.1 times 400. So 7,880. And the bottom number, which represents the unemployed, would be 0.02 times 8,000 plus 0.9 times 400, 520. Now, of course, vectors can have three components. So in example 3 in the book, it says a naturalist is studying 3 neighboring groups of animals. The sizes of the populations varies as the individuals move between the 3 groups. Let the 3 vector P naught, so P naught's a vector, be 100, 120, and 200. Give the sizes of the population at year 0. Suppose a year has passed. So now we have the populations after a year equals this matrix T, which tells us how the animals transfer over time, times the animal distributions at P naught. And we're told that this T matrix looks like this: 0.7, 0.2, 0.2, 0.2, 0.6, 0.2, 0.1, 0.2, 0.5. You'll notice all the columns add roughly to 1. Times P naught, which is our 100, 120, 200, and we want to find P1. Okay, so P1 would be, just do this multiplication. Our first entry in P1 will be 0.7 times 100 plus 0.2 times 120 plus 0.2 times 200, 134. 0.2 times 120 plus 0.6 times 120. Oops, I messed up. 0.2 times 100, because it's the second row, first column of the other matrix, which is a vector. So it's the second row here in this. So it's 0.2, 100, 0.6, 120, 0.2, 200. That we multiply and then add together. 132. And then 0.1 times 100 plus 0.2 times 120 plus 0.5 times 200, 134. So we can see that the animals are redistributed. Now let's find P2. So P2 will be this matrix again: 0.7, 0.2, 0.2, 0.2, 0.6, 0.2, 0.1, 0.2, 0.5 times P1, 134, 132, 134. And then using the calculator, we could find this fairly quickly. 0.7 times 134 plus 0.2 times 132 plus 0.2 times 134, 147. 0.2 times 134 plus 0.6 times 132 plus 0.2 times 134, 132.8. 0.1 times 134 plus 0.2 times 134 plus 0.5 times 134. And I got too many 134s. The second column, second row of the vector is 132, so it needs to be 132. It's 106.8. And so that shows us how we can get P2. So looking at example 4, suppose that a country's agricultural production is worth $75 billion. Its industrial production is worth $45 billion, and its services are worth $60 billion. We describe this with the production vector P, 75, 45, 60. Calculate C times P and interpret the result. Okay, and we're given also above the example that C tells us the consumption matrix, which tells us how the various parts of the economy are used. 0.1, 0.25, 0.12, 0.33, 0.11, 0.16, 0.21, 0.12, 0.42. And we're told to find C times P to find and then interpret the results. So P is the production in dollars, and C tells us the shares of the various sectors. So it says during the course of production, each sector consumes part of the production of all three sectors in the manner described above. So agricultural, industrial, and service. The first row gives the agricultural share in the consumption of the other three sectors. For instance, the 0.25 in the middle row says the agricultural sector consumes 25% of the production of the industrial sector. So the industrial sector might produce grain, and the agricultural sector needs some grain to work. So they're interdependent. The production, which is in the column, this is the total production, is used by the various, consumed by the various industries themselves, okay? Okay, so then we calculate this. So that's the first step, is do the calculation. So 75. Oh no, we got to remember the matrix C on the right is the thing we're multiplying on the left. Should write this out. And what we're wanting to find is C times P. So this is C, and P was 75, 45, 60. So we're going to multiply these two matrices, although we can also call the thing on the right a vector, the matrix and the vector. So 0.1 times 75 plus 0.25 times 45 plus 0.12 times 60, 25.95. That tells us how much the first industry consumed of the production of the first industry. 25.95. Okay, so that's how much of the first industry's product or production went towards consumption to the other industries. That's what this 25.95 tells us. Looks like I may have gotten the number wrong here. So it's 0.1, 0.75, 0.25, 45, 0.12, 60. 0.25 is, I see it, Very interesting. So it looks like the book has some typos in the The C matrix in the middle shows these values, but in the problem, in the example, it shows 0.15 and 0.22. So we'll pretend that these are the right numbers and that the matrix above is wrong in the middle. Okay, so that would mean 0.15 and 0.22. And that gives us 27.45. So why we have erasers. Now, 0.33 times 75 plus 0.11 times 45 plus 0.16 times 60 is 39.3. And 0.21 times 75 plus 0.12 times 45 plus 0.42 times 60. The last row is 46.35. So this tells us the first industry, which might have been agriculture, produced 75, but 27.45 of the $1 billion went towards consumption by the three sectors, which includes agriculture. So some amount of the agricultural production goes back into itself. Okay, so now we're told to find the surplus. The surplus is what remains after what has been consumed in production. So P minus C times P. Okay, so we found C times P. Which is our sort of our consumption vector you could think of. The surplus vector is subtract what we produced minus what was consumed here. So we know what P is. It's 75, 45, 60, and we know what C times P is. 27.45, 39.3, 46.35. So now we can calculate the subtraction. We just subtract each element from the other element. So it's straightforward. It's just 75 minus 27.45, 47.55 billion dollars of production, of surplus, I mean. And then subtracting these, we get 5.70, and the last 60 minus 46.35 gives 13.65. So that's the surplus in billions of dollars, which tells us how much was left over. So this would be essentially the actual production that's used up by everyone that's not in these industrial sectors.